In this lesson, we will talk about the infinite solution sets when trying to use inverse trigonometric functions arcsine, arccosine, and arctangent in order to try to find all solutions for the values of theta. Below are the solution sets for the trigonometric functions when solving for all angle measures theta given a real ratio c. Note that the reciprocal trigonometric functions will work the same as their reciprocal counterparts. What that means is when working and establishing what arcsine will look like for the solution sets, arccosecant will look the same. That is also true for arccosine and arcsecant, as well as arctangent and arccotangent. You can use the same methods to establish both solution sets. When working with arcsine, in order to evaluate all values of theta for sine of theta is equal to c, the first solution set is simply made by finding arcsine of c and then considering any coterminal angle measures of that by adding 2 pi k. In all instances in this case, we are going to consider k to be an integer, so k could be any integer. However, that is not all possible solutions. For example, if we were evaluating sine of theta would equal 1/2, this solution set would find all the answers in quadrant 1 as well as any of their coterminal solutions. However, there are more solutions for where sine of theta would equal, say, 1/2. The second solution set made for arcsine would be established by taking pi minus arcsine of that ratio c plus 2 pi k. This will work no matter what ratio you are working with, whether you are working with a positive ratio that originally would have an answer in quadrant 1, or a negative ratio that would originally have an answer in quadrant 4. The same applies when talking about arccosine. The first solution set for working with arccosine is simply just arccosine of that ratio plus 2 pi k. Again, k is an integer. However, the second solution set is made a little bit differently than the one for arcsine. The second solution set for arcsine is made by doing pi minus arcsine of that ratio c. For cosine, it is instead doing 2 pi minus arccosine of c. You could also consider this simply as negative arccosine of c plus 2 pi k. However, I recommend working with 2 pi minus arccosine of c, as this will more regularly result in answers starting in the unit circle, or between 0 and 2 pi, and then considering any coterminal angle measures past that. If you work with negative arccosine of c, you are more commonly going to have negative angle measures, which you may be less familiar with. Lastly, we have tangent. Tangent's going to be different than how arcsine and arccosine work. The reason for this is because of how sine and cosine work on the unit circle. Sine, for example, is positive in 2 adjacent quadrants, quadrant 1 and 2, and negative in 2 adjacent quadrants, 3 and 4. Cosine is similar. It is positive in 2 adjacent quadrants, 1 and 4, and negative in 2 adjacent quadrants, 2 and 3. Tangent, on the other hand, is not positive in 2 adjacent quadrants, but opposite ones. Tangent is positive in quadrants 1 and 3, and negative in 2 opposite quadrants, 2 and 4. Therefore, when trying to find the solution sets, we can actually combine what we would write before as 2 sets together into just 1 set overall by adding simply pi k. The solution set when working with tangent of theta is simply arctangent of that ratio c plus just pi k. This should also connect to the trig functions and their periods, where sine and cosine we established have a period of 2 pi, whereas tangent has a period of pi. These infinite solution sets, as said before, will also apply to the reciprocal trigonometric functions. So for example, if you want to work with cosecant of theta equals a ratio of c, the infinite solution sets would be arccosecant of c plus 2 pi k, as well as pi minus arccosecant of c plus 2 pi k. However, it tends to be recommended when working with cosecant, secant, or cotangent to carefully change them into sine, cosine, and tangent instead.